This is the video to accompany our paper, Look Ma No Hands, Agent Environment Factorization of Egocentric Videos. Egocentric video has the potential to be extremely useful for many computer vision and robot learning tasks since it is abundant and showcases diverse ways humans interact with their environments. However, the presence of the human hands in these videos adds a layer of complication. Consider a task like object detection. Human hands will frequently occlude objects of interest, making their detection much more difficult. However, the presence of the hand may be useful for the detection of commonly held objects. When predicting affordances from video, the goal is to predict where a human hand might touch a given object. Unfortunately, the images which give supervision show a human hand directly in contact with an object, but test time images would show only the object with no hand. Finally, when using these videos for robot learning, the motion of the human hand through the scene as it approaches different objects is critical information. However, there's an obvious visual domain gap between the appearance of the human hand and a robot end-effector, making transfer across these domains difficult. In this work, we propose a factorized representation which utilizes the novel diffusion-based video Inpainting model to produce high-fidelity images with the agent removed. As we will show, using a factorized representation helps mitigate these issues, improving performance on these applications. We propose a pixel space factorization of egocentric videos into agent and environment representations. For every frame, we produce two images, one which contains only the agent and one which contains only the environment with the agent removed. To produce these factored representations, we start with an input sequence of images. Next, we use off-the-shelf or easily fine-tuned semantic segmentation models to produce a segmentation of the agent. The input frames, along with the segmentations, are passed into our video Inpainting diffusion model, which is able to inpaint the regions of the image occluded by the agent, yielding a high-fidelity image depicting the environment without the agent. This, along with the image of the agent extracted using the mask, produces a factorized representation enabling powerful downstream applications. Agent environment factored representations can be applied to many downstream tasks. For visual perception tasks, such as object detection, the unoccluded environment image can be used in combination with the original image. For affordance learning tasks, the unoccluded environment can be used to predict relevant aspects of the agent in the agent representation. For reward learning tasks, the agent representation can be transformed into an agent-agnostic format for more effective transfer across embodiments. At the core of our method is our video Inpainting diffusion model, designed to leverage both information from surrounding frames and strong priors built from pre-training on large datasets. Prior work on single-frame Inpainting diffusion models starts with an input image. This image is embedded into a latent space using a vector quantization encoder, and then concatenated with the mask of the region to inpaint along with the noise target image, which represents the diffusion target. These spatial features are passed into a U-Net architecture which stacks blocks consisting of convolution and self-attention layers. Finally, at the end of the U-Net, the model predicts the noise added to the training target. We extend this model to process multiple frames of a video. Each frame is embedded into the latent space of the VQ encoder and concatenated with the mask corresponding to that frame and the noisy target image. Convolutions happen in parallel for each image, but all image features are concatenated together before attention layers, allowing the model to attend across images to copy the appearance of occluded regions if necessary. Finally, spatial features from all images are collapsed down to a single image by 3D convolution before the model outputs the predicted noise. We compare our method against diffusion-based single-frame inpainting methods and the state-of-the-art video inpainting method. In comparison, our method achieves the strongest PSNR, SSIM, and FID scores while maintaining a competitive runtime. By attending over previous frames, our method is able to accurately reconstruct objects which have been partially or entirely occluded, such as the panhandle or oranges in these examples. Here are some visualizations of the inpainting capabilities of our model. Note that the predictions are made on a per-frame basis with no special machinery for temporal smoothing. Our method is also effective for removing robotic end-effectors. Utilizing the environment agent factorization powered by our video Inpainting diffusion model, we are able to improve performance on a variety of downstream tasks. For object detection, we improve mean average recall from 0.26 to 0.38. For predicting grasps afforded by objects, we improve average precision from 0.35 to 0.41. And when learning robotic reward functions from in-the-wild human videos, using the factored representation improves the Spearman's rank correlation of the learned reward function from 0.56 to 0.61. Finally, we show that our factorized representations allow for simpler transfer across embodiments. In a real-world robot learning experiment, our agent is able to learn to open a drawer using reward derived exclusively from in-the-wild human demonstrations. We find this learning is greatly accelerated by using the agent environment factored representation. In conclusion, in this work, we developed a powerful video Inpainting diffusion model. We leveraged this model to produce agent environment factored representations and demonstrate that these representations can improve performance on downstream tasks. Code, data, and models will be released. Thanks for watching.